Well, hello everybody. Welcome to another day of algebraic structures. If you guys remember from last time, yay, thank you team. Hey there. Alright, so last time we talked about generators and cyclic groups and then groups generated from different sets. And where we left off was we were going to talk about direct products. So with direct products, what we'll do is we'll be making new groups from old groups. In particular, what a direct product is if we have two groups A and B, we're going to define the direct product as our new set is just going to be the Cartesian product. So that is, our set will consist of ordered pairs where the first entry is from the first group and the second entry is from the second group. We then define our operation component-wise. So that is, we just multiply or add, depending on what operation we're using, with the first entry by the first entry and the second entry by the second entry. What I want to show here is that if we do that, we'll end up with a new group. And that, furthermore, this group has cardinality of the cardinality of A times the cardinality of B. To start off with, the fact that the cardinality is the cardinality of A times the cardinality of B actually follows from work you would have done in 300, for example, because if you take the Cartesian product of two sets, the new cardinality is just the Cartesian or the product of the cardinality of the sets. So that one I won't focus on giving a proof of because we should have seen it before, but I do want to show that A cross B is going to be a group. So if we want to show A cross B as a group, what do we need to show? Well, first we need to show that in the end we need to show it satisfies the group properties. So the first thing we need to show is that it's closed under products. And so what I'll say is, let's suppose I have A1, B1, and A2, B2, and A cross B. Then what I want to show is that if I multiply them, I end up back in the same set. So now if I multiply these two, what I end up getting is we're going to do component-wise multiplication. So I get A1 times A2, and then B1 times B2. So if I take these and multiply them, I get this. Now what I want to point out is I want to show that this is in A cross B, so that means that I have to show this element is in A and this element is in B. But notice that A1 and A2 are both elements of A by definition. So if I multiply elements of A, what do I get is another element of A because A is a group. And if I multiply two elements of B, I get an element of B because B is a group. So in the end, what I get is that this is an ordered pair with the first entry in A and the second entry in B. So this is just an element of A cross B. So we've shown that A cross B is closed under multiplication. Does that make sense so far? Correct. The cardinality is just the number of elements in the group. So if I had 5 elements here and 10 elements here, then the cardinality of A cross B would be 5 times 10, as I'll end up with 50 elements. And just a quick go through of, again, why this is going to be true. Is because what I end up with are all my elements are of the form something in A, something in B. So what I get is I get the cardinality of A choices for the first one, the cardinality of B choices for the second one. Each one of those is going to lead to a distinct option. So if I want to find the total number of distinct elements, I just take the options here times the options here, which is precisely just the cardinality of A times the cardinality of B. So if we want to find the total number of elements, we can just multiply the number of elements in each set. All right, so you guys can help me out here. After closure of the operation, what else do we have to prove for a group? So exactly right. We have to prove associativity. So we have to prove that then the product is associative. So what we're going to have is three elements. Let's say A1, B1 times A2, B2 times A3, B3. And now I'll put the parentheses here to begin with, and I want to show that I can move the parentheses over. So how is this going to work? Well, what we're going to get is A1, B1 times, and if I multiply these, I get A2, A3, B2, B3. And if I multiply again, what I get is A1 times A2, A3 times B1 times B2, B3. I think someone's mic is open there. I hear some typing in the background. I don't know if you can put it on push to talk or something. Well, it's not a problem. I was just letting you know. All right. So now if we look at this, what I'm trying to point out here is that if I multiply these, I get this thing here. So I'm just following the order of operations, but what we notice is that in A, we know that we are associative. So what we can do is we can change the parentheses, and we just get this. And in B, we have associativity, so we change the parentheses, and we get that. And so if we work our way backwards, what this is just, well, this is A1 times A2, B1 times B2, so we get A1, A2, B1, B2 times A3, B3. But then this is just A1, B1 times A2, B2 times A3, B3. So because each of the groups was associative to begin with, we get the direct products will again be associative. So when we find a direct product, we know that we're still closed under our operation, and we have associativity, so we're on our way to making this a group. There were two more things we need to check, though. What were the other two things? That's exactly right. So we need to find the identity. And the easiest way to find the identity is just guess what it's going to be. What do we think the identity is going to be? Well, I'm going to say it's going to be the identity on A, the identity on B. If I take this element, I claim it's the identity on the Cartesian product, because now if I multiply by any element AB, what I get is the identity on A times A is just A. Identity on B times B is just B. If I switch the order, I get the same thing. So in fact, our identity element is just going to be the ordered pair where each element is the identity of the respective groups. So we will have an identity. In the same way, we can find inverses because I know that A has an inverse. So if I take the element A inverse B inverse and multiply by AB, I just get the identity on A and the identity on B. If I switch the order, I get the same thing. So if I just component-wise find the inverses, the ordered pair consisting of the component-wise inverses will give me the inverse in the new group. So what we have is we have two groups A and B, and what we can do is we can construct a bigger group by taking the Cartesian product. And so if we take, or the direct product, so if I take the direct product, I end up with a new group. So this is one way to take smaller groups and make bigger groups. Does that make sense to everybody so far? All right, so what I want to do now is just look at a couple examples here and say, what would Z2 cross Z3 be? Or Z3 cross S2? Well, if I actually wanted to list out all of the elements of this set, what I would do is I'd list the elements of Z2 as just 0 and 1, right? Z3 is 0, 1, 2. So if I wanted to find the elements of this set, it would be things of the form 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, and I believe that's all of them, and I can check I should have how many elements? 6. I do have 6. So this would be all the elements of Z2 cross Z3. Now, another thing we might want to do is make a Cayley table. I'm not going to make the full table, but I would want to think about what do some of these look like. So let's just look at a couple of these. I'll make a partial table here. And so now my operation is going to be the addition on my component-wise addition. So what would 0, 0 plus 0, 0 be? Well, that's just 0 plus 0 is 0, 0 plus 0 is 0. If I take 0 plus 0 is 0, 1 plus 0 is 1, I get that point there. Now, let's say I take 0, 1 plus 0, 1. I'm going to get 0 plus 0 and 0, and 1 and 1 is 2. But if I take 0, 1 plus 0, 2, I get 0 and 2 plus 1 is 0 in Z3. So again, I'm going to fill this out just as if I'm just adding component-wise. And notice I have to remember what the addition was in the original set so that when I'm taking 1 plus 2, I get 0 instead of 3. So I end up back in this set. And again, you can fill out the entire Cayley table in this manner so you know exactly what Z2 cross Z3 is going to look like. Does that make sense? Questions in there? Let me ask a question here. So the identity on the set is going to be what element? So the identity is 0, 0, right? What's the inverse of 0, 1 going to be? So not 1, 0, because if I take 1, 0 plus 0, 1, I get 1, 1, right? But for an inverse, I want the identity. So I'm asking, what do I add to this to get out 0, 0? So 0, negative 1. 0 plus 0 is 0, negative 1 plus 1. That is correct, but not quite, because remember, negative 1 isn't explicitly in Z3. And what is negative 1 in Z3? Remember, that'd be 2, wouldn't it? So if I subtract 1, that's the same as adding 2. So I want to use the element in here. So I would say 0, 2 plus 0, 1 is 0, 0. So 0, 2 would be the inverse of 0, 1. And so in general, if I take this, what I want is the inverse of, say, AB. Remember, is going to be, I find the inverse of A and the inverse of B. So going back to my last example, the inverse of 0 is 0, and the inverse of 1 is 2 in Z3 anyway. So my inverse there was 0, 2. Does that make sense? All right. So again, we have to start thinking in things in a little bit different way. We're dealing with, the integers mod 2 and 3 and whatever else instead of just the integers, so we have to remember how the inverses work there. I think my next one was Z3 cross S2. Z3 we already said was 0, 1, and 2. What is S2? Completely forgot what that means. We did have S3 on the test. Very good. I'm glad you're at least remembering it's there. It's the permutations on a 2-element group. Very good. I know that was an unfair question, maybe. That's why I did it. Is because it has been a while. I'm trying to remind you. This is all the permutations on a 2-element set. So if I wanted to write those, remember, I could have 1 goes to 1 and 1 goes to 2. Otherwise, I could interchange these two, and those would be the only permutations. And so what we could do is, if we notate those using cycle notation, that would just be 1 and 1, 2. So the elements of S2 are just the identity, and 1 goes to 2, 2 goes to 1. Does that make sense? So now if I take the direct product of these two, what I get is just the set that looks like 0, the identity, 0, 1 goes to 2, 1, the identity, 1, 1 goes to 2, and 2, the identity, and 2, 1 goes to 2. So we'll have those 6 elements again because we have 3 by 2 elements, so we end up with 6. And then let's just look at one example. Let's take 1, 1, 2, composed with 2, 1, or the operation here. Well, now the thing here is that the operations are actually different between these two sets. So what we end up with is this is actually addition. So we're going to get 1 plus 2 in the first case, but we're going to get 1, 2 composed with 1 in the second case. So what we end up with is 1 plus 2 is 0, and 1, 2 composed with the identity is just 1, 2. So even though we have different operations between these sets, we still can treat this as component-wise operations. So here I have addition, and here I have composition, and I can still calculate what that's going to be, and I still end up with an element of the set. Does that make sense? All right. So now to point out, the identity here is going to be 0, the identity mapping. If I want to find inverses, the inverses of 0 is 0, inverse of identity is identity, inverse of 1 is 2, inverse of 2 is 1, and the inverse of 1, 2, it's itself. So if I wanted to find, say, the inverse of this one, the inverse of 1 is 2, the inverse of 1, 2 is 1, 2, so the inverse of 1, 1, 2 is 2, 1, 2. And so we can find, again, identities and inverses just like we would for a normal group. We just do that component-wise to get out each of those and what they're going to be. All right. All right, so again, the point about direct products there is that they're going to form bigger groups from smaller groups. And if we can take bigger groups and write them as direct products, then we can focus on what the smaller groups are so that we can get... Go ahead. Mm-hmm. So are you trying to switch the ordering of the pair or switch the order that I wrote them in? Right. So what I have to have is I can't switch the order here. So this would not be equal to, say, this, because that's a distinct element. Because remember, for Cartesian products, the order matters. So when we're taking direct products, the order matters because it's an ordered pair. So these two would not be the same. In fact, this element would not be in here because this is saying a permutation is a part of Z3, which is not actually correct. So we do have to be careful when we're doing this. These are things in Z3. I'm adding in Z3, so I end up in Z3. All right, very good. So yes, that's right. We do have to be careful about the ordering. Just like with direct products in general, the pairs are ordered, so it matters. All right, so, and that's what I'm going to leave you with for direct products. Is there's just some examples in the homework to go through. So I'll let you look at those and kind of we'll use these to build up new things. And a lot of what we've been doing is either breaking big things into small things or small things into big things. And this is one new thing that we can use to take small groups and make big groups. All right. Alright, so we had done most of that section last time. So now we're going to move on actually to the next section, and that is we'll be talking about cosets. And so what is a coset? So very good. It does have the word set inside, so it is going to have some type of set. And what we're going to be doing with cosets is looking at different sets based on different subgroups. And so what we're going to have is, in order to talk about cosets, we're going to first define H as a subgroup of a group G. So we'll have a group G, we'll have H as a subgroup, and then we're going to define a relation, which I'm just calling this equivalent here. And I'm going to say A is equivalent to B if AB inverse is in my subgroup H. And what I claim here is that is an equivalence relation. So the first thing we should do is actually show that's an equivalence relation. So what do we need to show if we want to show that's an equivalence relation? Now we're going way back. Very good. So it has to be reflexive, symmetric, and transitive. So the other thing was it has to respect the operation if it's a congruence relation. I'm not making the claim this is... Yes, so at the end we would have to show it respects the operation if we wanted to show it as a congruence relation. But I'm not actually making the claim this is a congruence relation yet. I'm just making the claim that it's an equivalence relation. So we just have to show reflexive, symmetric, and transitive. So let's show that A is related to A. What that means is I have to show that A inverse is in H. What is A inverse equal to, though, is the identity. Does the identity have to be in any subgroup of G? Yes, it does. Why? Well, because H is a group, so it has to have an identity. And we showed that for subgroups, the identity of the subgroup is the same as the identity of the group. Therefore, the identity on G has to be in any subgroup. So for any subgroup, A inverse has to be in H. Makes sense? The next thing we have is if A is related to B, we have to show that B is related to A. So that is, we know that AB inverse is in H. We have to show that BA inverse is in H. Does that make sense? So how would we do that? How would I show that this is an element of H? Well, does this look similar to this at all? It looks like a reverse. So I know this is an element of G, and I want to show that this also has to be an element of H. This is actually a specific element of G. How does this relate to this? Well, notice what happens if I multiply by AB inverse. What do I get out? I would just get the identity, so that cancels the identity. So I'm just left with the identity. If I do it the other way, I'm going to get the same thing. So what that really says is that BA inverse is actually equal to AB inverse inverse. That is, this element is the inverse of this element. Do you guys see that? So the point here is that H is a group. So is H closed under inverses? Yes, H is closed under inverses because it's a group. Therefore, if AB inverse is in H, necessarily the inverse of that has to be in H. So therefore, if AB inverse is in H, BA inverse has to be in H. Therefore, if A is related to B, B is related to A. So we have reflexive and symmetric so far. The last thing to do is show transitive. So let's suppose A is related to B and B is related to C. We then need to show that A is related to C. So this means that A, B inverse is in H, and B, C inverse is in H. And I have to show that A, C inverse is in H. So how am I going to do that one? Well, notice that A times C inverse is equal to, well, if I just multiply on the inside here by B, B inverse, what is B, B inverse? The identity. Right. I actually want to do it the other direction. I do B inverse B, sorry. But either way, it's still the identity. So if I take A times the identity is just A, times C inverse is still the same thing. I haven't done anything because I've multiplied by the identity. However, due to associativity, what I get is A, B inverse, B, C inverse. What do I know about this element? Well, that's in H. What do I know about this element? That's in H. So if I take two things in H and multiply together, do I get something in H? Yes, indeed I do, because H is a group. Therefore, I do get that A, C inverse is in H. So what we get is that this A is related to B if A, B inverse is in H is indeed an equivalence relation. Does that make sense? All right, very good. All right, now with that equivalence relation, what we want to talk about are what do the equivalence classes look like? And the equivalence classes we're going to say are going to look like HA, that is the set of H times A such that H and H. If that is equal to HB, then A is equivalent to B according to our last equivalence relation, if and only if those things are equal. So the equivalence relations of A we're going to call right cosets of H, because we take H and multiply on the right by an element, and that's what we call a coset, or a right coset rather. So this set is a right coset, and HB is a right coset, and then we're going to say that A is related to B by that previous relation if the cosets are equivalent. All right, so let's go ahead and show what we're talking about there. So let's suppose that A, B inverse is in H. What we want to show is that HA is equal to HB. And then we want to show if HA is equal to HB, then A, B inverse is in H. So we do want to show both directions. So we're saying that this is going to give us another way to look at whether or not these things are equivalent according to this relation. All right. So now, if A, B inverse is in H, then what I would have is, let's just start with HA, is a set of all elements of the form H times A such that H is in H. Does that make sense to everybody so far? All right. Now, what I want to do is I want to show that this is equal to HB. So somehow I have to get this is equal to the set of all H times B such that H is in H. So how am I going to do that? Well, what I want to note here is I'll stick with this thing, but if I take this and multiply by B inverse B, would this be the same set? Yes, it would, because I've just multiplied by the identity, right? So I'm saying this is all the things of the form H, A, B inverse B such that H is in H, because that is exactly the same as HA. However, what I know is that this is an element of H, isn't it? And this is an element of H. So what is this going to be equal to? Some other element of H. So what we get is an element of h times an element of h is a different element of h, but we get an element of h times b such that, and this is just some element of h. So what we get here is, indeed, because I can take HA and multiply by B inverse B, and I get HB, so HA is equal to HA, B inverse B is equal to HB, we get that those are indeed the same. And if these are the same, then again, we can show that by reversing the order that A, B inverse will have to be in H. So we'll get that these two relations, the right cosets being equal, is equivalent to saying A, B inverse are in H. So we have two different ways to look at this equivalence relation. Is that okay with everybody? And so what we're pointing out here is that if we want to find the equivalence classes, or that is if we want to partition our group up, our group will be partitioned into the equivalence classes of each element A, and all of those equivalence classes are going to look like right cosets. So all of the equivalence classes will be right cosets of H. So what we can do is think about, well, each of these right cosets then, because this is an equivalence relation, forms a partition. So every right coset is either equal or it'll be disjoint from each other. So there's either no overlap or complete overlap. And so we can break that up into different sets, and we can talk about each of the cosets of our group to give us a different way to kind of break it down into smaller parts. All right, so now let's actually look at an example and see how that works out. Let's suppose that I have G is the integers and H is the group generated by 7. So that's going back to our last lecture. What would the right coset of H look like? So what would H plus 3 look like? I'll let you guys think about that and see if you can give me an explanation. Very good. So H will be elements of the form 7 times an integer. So very good. So H plus 3 will just be all the things of the form 7k plus 3. So it'll be the set consisting of 3, 10, 17, 24, and you can go backwards too. So -4, -11. And so it'll look like all the things that are congruent to 3 mod 7. And so that's what my left coset would look like. If I wanted to find other cosets, notice that H plus 0 would be a right coset, and that's just H, because that's all the multiples of 7. H plus 1 would be everything congruent to 1 mod 7. I could go 2, 3, 4, 5, 6. And so we could talk about the different cosets, and each of the different cosets are going to form each of the numbers modulo 7. Does that make sense? Should never be sorry to ask a question. The coset for this one? All right. So let's actually, I'll write that up at the board because that'll make it easier. But what we have was H is equal to all the things of the form 7k such that k is an integer. So H plus 3 is just going to be, if I take things in here and add 3, so that's going to be everything of the form 7k plus 3 such that k is in Z. So what that looks like is, well, if I plug in 0 here, I get 3, 10, 17, dot, dot, dot. but I can also subtract 7, so I'd get -4, -11, ... And so I would get all the things that are congruent to 3 mod 7. So this is all x such that x is congruent to 3 mod 7. So that would be my description of the right coset with 3. Now if I think about the different cosets that are available, I could have h plus 0 is just h, are the multiples of 7. H plus 1 would be distinctly different, and that would be all the things that are congruent to 1 mod 7. If I follow the same process, and I said h plus 2 would be all the things congruent to 2, 3, 4, 5, and 6 we can do. And so what we end up with is that there will be 7 distinct right cosets. Each one is going to be the elements that are congruent to whatever element this here is mod 7. Is that okay? Not a problem. And never be afraid to ask a question. That's why we're here, is I want to know what you're thinking. All right, so with that said, though, what I do want to look at is, let's make G a little bit smaller, so let's make it finite. Let's call it Z12. Let's let H be the group generated by 4. What I want to do is actually list all the right cosets of H in G. So the first thing, I'm going to let you guys try to work on this on your own, is the first thing you should do, though, is find what does H look like. So help me out there. What does H consist of? Well, the group, so 4K. Very good. But 4K within Z12 is going to be what? We'd have 4, and then we'd have 8, and then we'd have 0, and then 4 and 8. So all the elements of the form 4K within Z12 are just going to be 0, 4, and 8. Does that make sense? And then from there, I'm just going to go through all the elements of Z12 and say, okay, well, what is H plus 0? What is H plus 1, H plus 2, H plus 3, H plus 4, 5, 6, 7, 8, 9, 10, 11. So I'll give you guys a minute to try to figure out what each of those looks like. And I'll write some of that up there while you're thinking. I ran out of room after 5, so I'll stop there. All right, so help me out here. What is H plus 0? That means take the elements in H, each of them, and add 0. So I get the set consisting of... Very good, thanks, James. So I get 0, 4, 8. What does H plus 1 look like? Very good. What does H plus 2 look like? Very good. All right, so I'm just going to keep going through. H plus 3 is 3, 7, 11. What's H plus 4? 4, 8, 0. H plus 5 is 5, 9, 1. What do we notice about H plus 4 and H plus 5? Well, H plus 4 is just H plus 0, isn't it? And H plus 5 is just H plus 1. No, they're actually the same, because remember, ordering for sets doesn't matter. So 0, 4, 8 is the same as 480. So these two are actually the same set. And these two are actually the same set. And if we find h plus 6, that's just going to be h plus 2. H plus 7 is just h plus 3. So if we find h plus 0, h plus 1, h plus 2, and h plus 3, we actually have found all right cosets of h within Z12. So we're going to have 4 distinct right cosets, each one's consisting of 3 elements. And so actually that is something surprising. Each of these right cosets have the same cardinality, don't they? Do you guys think that's a coincidence, or is that always going to happen? Always? Always? All right. So indeed, that is always going to be true. And actually, that's the next thing that we're going to look at, is that in general, if we find any right cosets, their cardinality of any right coset is going to be exactly the same as the cardinality of the original subgroup. And so what I want to say is, if H is a subgroup of G and A is in G, then AH, or HA rather, is equal in cardinality to H. So how would I prove that? How could I prove that the cardinality of H is equal to the cardinality of HA? Well, if I want to show cardinalities of sets of the same, what I can do is find a one-to-one onto mapping. And then, by definition, if I can find a one-to-one onto mapping from this to this, their cardinalities are the same. But remember, we're one-to-one and onto if and only if we're invertible, right? So if I can find a mapping, let's say alpha from H to HA, which is invertible, then that implies that the cardinalities have to be the same. So let's actually find that mapping. And I'm going to define alpha as alpha of x is just equal to x times a. Now, what I'd have to do is check through and make sure that this is well-defined one-to-one and onto. I just want to make sure first, is this a well-defined mapping? If I take something in H and multiply by A, do I end up with something in HA? So here, instead of using X, I can actually use an H. So alpha of H is equal to HA. So if I take anything in H and multiply it by A, I have to end up with something in HA, don't I? And I have to end up with a unique something because products are well defined within any group, and H is a subgroup of a group G. So this is a well-defined element of HA. Make sense so far? Now, instead of showing this as directly one-to-one and onto, I'm actually just going to show it's invertible. And I'm going to claim that alpha inverse from HA to H given by alpha inverse of, let's say, Y is equal to YA inverse. I'm going to claim that that's a well-defined mapping and that it's the inverse of this mapping. First off, is this well-defined? So if I take something that looks like HA and I multiply it by A inverse, what I get is something that looks like H, right? Therefore, if I start in HA, do I end up in H? When I started in HA, I got something in H, and it is uniquely defined because this is a group, so this is a well-defined mapping. So I know this is a well-defined mapping and this is a well-defined mapping. But if I take alpha composed with alpha inverse of Y, let's say, what I get is Y times A inverse times A, which is just Y. And if I take alpha inverse of alpha of H, I get H times H inverse is just H. So in both cases, the compositions of these give me what I started with, so they end up being the identity mappings. So these are inverse mappings, which means that this is an invertible mapping. And since it is invertible, it is a bijective mapping. It's one-to-one and onto, which therefore means that the cardinalities of these two sets have to be exactly the same. Therefore, since A was arbitrary, all of the right cosets will have exactly the same cardinality. So notice that what we ended up with is if we find the right cosets of any subgroup, we end up with a partition of our group where each of the sets within the partition have the same cardinality. They have exactly the same size. Now, before I move on, I do want to say just one more thing, is that we could also do, instead of right cosets, we could do left cosets. So if we wanted to do left cosets, what would we do? Well, instead of having A equivalent to B if AB inverse is H, we'd say if A inverse B is an H. And then a left coset would be AH or BH. And then we could go through and say 3 plus H instead of H plus 3. And we can go through again and say, okay, the cardinality of H is going to be the cardinality of AH. So for left cosets, all of the same results follow exactly the same as well, is that we can find left cosets and we can partition into left cosets or right cosets. Either way, we're going to end up with our partition of our group into equivalence classes, which are all the same cardinality. Questions on any of that? All right. Do you guys have enough for today, or do you want to keep going? All right. So there was one vote for I don't care what we do, and one vote for please let's stop. I know we still have a lot of time left in class, but I feel like there was a lot there. And I'm not going to push too hard since we're online anyway. So I'll actually, instead of starting off with Lagrange's theorem and cyclic groups, we'll get to that next time then, or next Monday. So I'm going to post some homework now, and I hope you guys will look at that, and that'll be due next Monday. I'm going to post it right now. I just wasn't sure how far we'd get. So then that will be due next Monday, and I'll put that on Blackboard. Do you guys have any other questions? Oh, you're welcome. Thank you guys for joining. You can do whatever you like as far as getting a hold of me. You can email me, would be a good way to do it. Otherwise, if I'm on Discord, you can just hop in and start talking to me. I'm on there often enough, even if I'm not in class. So just hop in and start talking to me. I'm happy to answer any questions you have. So however you would like to get a hold of me, any of those options are good. All right, with that then, I will let you guys go, and I will see you next Monday.